Physics students, welcome to the second video from subtopic 11.3 in the capacitance subtopic. And in my previous video, I spent a lot of time talking about capacitors and how they work and dielectrics, and especially how to deal with capacitors in simple circuits, capacitors in parallel and series. What we're going to talk about now in the next two videos is really sort of the meat of the whole topic of capacitance, and I'm going to explain in great detail why it is that we use capacitors in circuits. Most of the things that use electricity or electric current probably have capacitors in them. There's almost an infinite number of applications of things that we use capacitors for, okay? All right, so if we consider, again, a parallel plate capacitor, remember there's all different kinds of capacitors, and we're only going to deal with a parallel plate capacitor in this class. If we consider a parallel plate capacitor that is initially uncharged, okay, in order for current to flow through it, charge has to move between the plates, of course. We've studied electric fields before a long time ago, and we know that this requires work against the electric field, and that work is given by the magnitude of the charge times the potential difference, okay? And that's, of course, equal to, by the work-energy theorem, exactly equal to the energy acquired by the charge. Now, because capacitance, which is a constant for the device, is the ratio of Q over V, and that's a constant, and V equals Q over C, therefore, then a graph of V against Q would be linear, okay? All right, so this is just, I haven't really done anything. I've just messed around with this equation, and I've just graphed them, okay? Now, remember how we said that the total work done when we had a varying force through a distance? What we had to do is we had to analyze the graph and then take the area under the graph. It's kind of a similar argument here, okay? Because work is QV, okay, that's going to be, I have to differentiate because V is a function of Q, or what I have to do, differentiate, I have to integrate V of Q dQ from 0 to Q to get the total work done, okay? And that ends up being, once I do this, this integral, I end up with 1/2 Q squared over C, or in other words, that's the energy stored in the electric field between the plates, okay? You could also express it as 1/2 CV squared, 1/2 QV. It's all the same thing, okay? So that's actually where that equation comes from that's in your data booklet, and I believe the one that you're given is E equals 1/2 CV squared, but it's really all the same thing. So again, what we've done is we've derived, and you will not have to derive anything using calculus, of course, in this class, but we have derived an expression for the amount of energy that's stored in the electric field between two plates in a parallel plate capacitor, okay? All right, so here's one of many applications of a parallel plate capacitor. So a camera flash unit, flashes for cameras they all utilize capacitors. They all time the amount of energy released to make a really nice bright flash. We'll talk more about timing later. Okay, but let's say that we have a 150 microfarad capacitor at 200 volts potential difference. How much electric energy can be stored? Well, that's 3 joules. Okay, now that doesn't seem like very much, but the timing of the energy release, as I'm going to talk about in my next video, is very, very important. So for example, if the flash bulb discharges in, say, 1/1000th of a second, then the power output would be, of course, that's the work or the energy over time, and that's 3,000 watts, which is actually quite considerable, okay? How about this one? This is the kind of question you'll be asked a lot, where it's more of a qualitative question where you're given a parallel plate capacitor and you're asked to find, certain variables change. Well, how do certain other variables change? Okay, try this one. Okay, so it carries a charge Q and then disconnected from a battery. The plates are initially separated by a distance d. What happens if the plates are pulled apart until they get to a distance of 2d apart? How would the energy stored in the capacitor? Okay. Well, effectively, you have 2 different capacitors, right? Okay, the first capacitor is given by epsilon A over D. The second capacitor, which would be the case where we have 2D, a greater separation, would obviously be less than the initial capacitance, and it's exactly less by a factor of 1/2, okay? Now, Q doesn't change. The only thing that changes is the actual plate separation, okay? So since E equals 2Q squared over 2C, or 1/2 Q squared over C, the energy will now increase by 2 times. And my final line here is I'm actually doing that same sort of reasoning where I have initial energy, final energy, and it's going to be, because it's over C, the actual energy ends up increasing by 2 times. Okay, here's a slightly more difficult problem. Okay, we're going to start analyzing circuits again. Okay, so in this diagram I have 2 capacitors connected in a circuit. C1 has been charged by connecting to a 12-volt source. The other capacitor C2 is initially uncharged. When the switch is closed, the charge moves between them. Okay, so initially you have C1 that's been charged by a 12-volt EMF. C2 has no charge. Okay, now the way that this circuit is set up, there's no charge flows between these two, right? Okay, but when the switch is closed, then things are going to get interesting. And the first question is calculate the charge and potential difference for each capacitor after the switch is closed and charge no longer moves in the circuit. So in other words, you're going to find this out in the next video. Calculate the charge and potential difference when C1 completely discharges and C2 completely charges. Okay, all right. So the charge on C1 is given by Q1 C1 times V, 3.84 times 10 to the minus 5 coulombs. Now, when the switch is closed, charge moves from C1 to C2. Okay, so the potential difference across V1 or C1 will go down, and therefore the potential difference across C2 will go up. Okay, so if we note that V1 plus V2 is the total voltage, which of course is V1. Okay, because V2 had no potential difference initially, and by conservation of charge, Q equals Q1 plus Q2, that's also a constant. We can make this ratio, where since V1 equals V2, Q1 over C1 equals Q2 over C2 after the switch is closed and charge no longer moves. Then it's just an algebraic problem, okay? All right, rearranging a little bit and substituting. Okay, you want to follow my reasoning here. I'm not going to go through every single step with you because you have it right in front of you. I get that Q1 is 9.87 microcoulombs and that Q2 is 28.5 microcoulombs, okay? And we were also asked to find the potential difference across them. V1 and V2 are going to be the same in the end, and that's pretty easy to figure out because if there's whatever the charge is, whatever the potential is here, let me get my pen. Whatever potential is here on the right side of Q1, it's going to be the same as the right side of Q2, and that's going to be equal to what it is on the left side of C1 and the left side of C2. Okay, yeah, so that's pretty straightforward. Okay, all right. Now, part B: compare the energy stored before the switch is closed with the energy stored after the switch is closed. Now, before the switch is closed, I have a total energy of 1/2 C1. It's really V1 squared, right? Okay, which was the initial EMF of the battery that charged it, which is 2.3 times 10 to the minus 4 joules. Now, after the switch is closed, things get a little more interesting. We have to consider the energy of each capacitor, okay? And that ends up being quite a bit less than before the switch was closed. So you can see that energy is clearly not conserved in this situation. And the reason is because we always have a dissipation of heat in the connecting wires when charge moves through it. Okay, so in other words, wires heat up, and you know that from your studies of electricity so far. Okay, I'm going to talk about at this point I'm going to talk about only charging capacitors. Okay, discharging capacitors is in itself such a big topic that will be the third and final video in this subtopic. Okay, all right, and I've alluded to the fact before that that the amount of time it takes for a capacitor to get charged and to get that potential difference in that charge on the plates takes time, and that time is really important. Now, it's important because in order to effectively use capacitors in circuits, we need to be able to control and predict the rate at which energy is not only dissipated, but also builds up. And the two of them are intimately related, as you'll see shortly. Okay. Now, consider the following circuit. If we consider this capacitor initially uncharged, okay, there's a resistor in this circuit, and there's a potential difference over here. This is called an RC circuit. So when you hear that term RC, that means that there's a resistor and a capacitor. That's all that means. There's nothing mysterious, okay? And the switch is situated such that it can go from A to B and back and forth, okay? Okay. Now, when the switch is at A, the capacitor is building up a charge. What it's doing is it's getting energy from the potential difference of the battery. And it turns out that this resistor is important in this situation, okay? When the switch is moved to B, the capacitor will lose energy and discharge through this resistor, okay? Now, just a couple, I said there's lots of different applications of resistors or capacitors in circuits. Intermittent wipers use capacitors, building up of charge and discharging them in a certain amount of time, periodically. And pacemakers also have capacitors in them that have to do with pulse generators. So in both of these two examples, and in many others, the rate at which energy is discharged, it needs to be very regular and it needs to be dependable, and capacitors provide that dependability. Okay. All right. So again, let's really get into some numbers here, and let's actually apply some numbers to this example. So charging. So the switch is at A. Okay. All right. If the switch is at A, we have a current flowing. Okay. And the electrons move counterclockwise. So I'm going to talk about conventional. I'm going to refer to conventional current here. Okay. Which would be in this case, right? Conventional current is the positive charge moving. So what that means is that the top part of the plate becomes positive and the bottom plate becomes negative. Okay. Now, eventually, after enough time passes, the potential difference across the plates is going to equal the potential difference of the battery. Okay. Meaning that this resistor is really not important in that case. Now, in this case, if I were to graph V of t against t for charging, it takes about 10 milliseconds in this case with these numbers for the capacitor to fully charge. Okay, and you can see the shape of this curve should remind you of something that's exponential. Okay, now since Q is directly proportional to V of t, it's just multiplied the constant, the capacitance, then Q of t will have a very similar shape to V of t, or epsilon of t. I'm using epsilon and V interchangeably, as I often do. Okay. The only thing that's different is that we have a different values on the y-axis. Okay. Now, it turns out that the current actually decreases. Okay. And I'm going to talk a little bit more about current later. My entire leading you through this journey of capacitance, I'm actually making a lot of simplifying assumptions, and I'm not getting as deep into it as I could. It's much more complicated than I'm presenting here. I'm really only presenting to you what you really need to know to be successful in the IB and the IB exam. Current is a little more tricky. It decreases because the electrons on the negative plate end up, when they pile up, they push back any new electrons that try to get to that plate. But it turns out that it's an exponential function that goes down instead of up, like Q of t and V of t. Okay? Okay, so the same circuit here, all right? Okay, let's take even a closer look at the numbers. Okay, now the potential difference across the capacitor as a function of time is given by this equation. You don't need to derive this equation. I'm not going to derive it for you. It's fairly complex. It's a fairly complex derivation with calculus. And you're not given this equation, and that's because you do not need to deal with a quantitative treatment of charging capacitors in the IB, okay? Only qualitative. But I'm giving you the math here because if you can understand the math here, when we get to discharging, it'll be a piece of cake for you, okay? All right? So this particular function is given by V naught times the quantity 1 minus e to the negative t over RC, and e is the natural logarithmic function, okay? And where V naught is the EMF of the battery, T is time, R is the resistance of the resistor in the RC circuit, okay? And C is the capacitance of the resistor in the RC circuit. Now, this product RC, which you're going to see in a lot of these equations as an exponential, is so important. It's called the time constant, and it's called tau. And tau, the Greek letter tau, it determines the time scale for the charge and the discharge of a capacitor. So the greater tau, the longer time it will take to charge and discharge. It takes the same amount of time to charge as it does to discharge for any particular capacitor, okay? In this particular example, tau is 0.002, and you can see that the units are ohms times farads, okay? Now, for example, if we look at this graph, we can confirm that, okay, so taking t at, say, 2 milliseconds, if we plug it into this equation, we get that V at 0.002 is 3.79 volts, and you see that's exactly what this graph shows, okay? Okay, now, it turns out that charge, because charge, remember, is just the potential difference multiplied by the capacitance, again, it has a very similar shape. We can, by the way, Q naught in this equation is the maximum charge in the capacitor, okay? So it's C times the potential difference across the battery, or the EMF of the battery, okay? And in this case, it's 12 microcoulombs, okay? And then again, just picking a random time I did here. I did 4 milliseconds right here, and I got Q of 0.004. I got 10.4 microcoulombs, which is right there, so you can see that that agrees with this graph, okay? A couple of very important points, all right? Tau is the time required for the potential difference and the charge on the capacitor to reach 63% of the maximum. And we can see this, and I hope that your mathematics with natural logs is sort of up to date here. We can see that because this factor that we use to multiply the maximum charge and the maximum potential difference, you can see that if t equals tau, then this exponential becomes a -1, and it ends up being 0.63, okay? You should be able to show also that the units of tau are those of time, okay? That's a classic IB question, all right? And you can see that an ohm times a farad, since an ohm is a volt per amp and a farad is a coulomb per volt, you see that we end up with a coulomb per amp, and an amp is a coulomb per second. So then we have 1/1 seconds, which is a second. You do not need to be able to derive all of these equations, okay? And you need to deal with charging capacitors graphically, qualitatively. You're not responsible for these equations when it comes to charging capacitors, all right? Let's do a quick example to round out this video, okay? So we have a graph of Q of T against T for a charging capacitor. It's shown. Okay, these are the same numbers I had before. Use the graph to estimate the EMF of the, maybe these aren't the same numbers. Anyway, I give you the numbers. Use the graph to estimate the EMF of the battery. Well, from the graph, you can see that the final charge, the greatest charge you ever get, is about 36 microcoulombs, okay? And then you know that, that Q equals C times the EMF of the battery, okay? That the biggest charge you'll ever get is C times the maximum voltage of the circuit, which is the EMF of the battery. Solving for V, it's Q over C, and I get that it's a 9-volt battery, okay? And a graph of I of T against T, as we said before, the current drops off exponentially, all right? And you notice how it drops off in the same amount of time as it took to obtain that maximum charge, okay? And the initial current we can see, which is I at 0, which is actually epsilon over R. That's 9 volts over the resistance, which was given, and that's 0.0045 amps, which is this value right here,